Alright, so what is, let me get this. Alright, what is the formula for finding the slope of the tangent line to the curve y equals f of x at the point P A f of A? So this is kind of the general, they want you to find some kind of generalized formula. And what we're going to look for here is point slope form. Oh, sorry about that. That looks kind of messy. So we're looking for point slope form. And what that looks like is, I have a little add-on here. Is this right here? Let me kind of move that out of the way. Alright, yeah. So I have this little add-on here. This is like a general formula. So we're going to apply this to what we see up here. We're just going to rewrite this point slope form. We're just going to rewrite that with these variables. And just know that it doesn't give you any definitions for y or x, because these are just general terms that we'll always include. So we're going to have y minus, when y1 here is going to be the y value, which is f of a, so y minus f of a equals the slope here. Well, we want to just write m, but we got to remember the slope is the derivative, the output of the derivative at the given point a. So that is written just f prime of a times x. Remember, there's no definition for this term, so it's just a generalized term, x minus x1. x1 is the x coordinate, so that in this case it's just going to be a. And so this is the answer for number 1. And we'll notice over here I have in Desmos, I've already typed in the function for number 2. It's not the answer, it's just a function, a starting point. You'll see I'm going to take it a step further than where it wants us to go really quick for number 2, just to kind of show you something cool on Desmos. Alright, so it wants us to use this formula, the point slope form, to find to find the slope of the tangent line to the graph of f of x equals x squared plus x plus 1 at the point where x equals 2. Now where I just took it is a little bit already passing where it wants us to go. You'll see it to find the slope at any given point, as we already shown, is just going to be f prime of a. And so what we're going to do here is, so we have is just get f prime of x. We have f of x equals x squared plus x plus 1. Well, we can just do f of x equals Leibniz notation, the derivative with respect to x of x squared plus x plus 1. And we can see this is a pretty easy one. So d dx of x squared equals 2x. d dx derivative with respect to x, of x equals 1, and the derivative with respect to x of 1 is just a constant, there is no x, so it equals 0. And so this can just, the derivative f prime of x can just be written f prime of x equals 2x right here plus 1. Alright, let me rewrite this kind of looked a little like a plus. All right, 2x plus 1. And so to find the slope of the tangent line, you're just going to plug the given value. You want to find the slope of the tangent line at where x equals 2. You're just going to plug that in. So f prime of 2 equals 2 times 2 plus 1. So f prime of 2 equals 5. And that would be the answer. So we just used the f, just really the f prime of a right here to find the f prime of in this case the f prime of x. We plugged it in. We plugged the x value that it wanted in and got the slope right there. So the cool thing about this is now we can use this. We can put this slope. That was the only piece that we were missing for the point slope form, and we can plug that in, and we can just say, oh, okay, y minus well, to get the y value is by just plugging the given x value into the original equation. So it told us, it gave us x equals 2. So we can just plug that in and say 2 squared plus 2 plus 1, well, that equals 7. So we have our y1 here is going to be 7, and this is just following the layout here, equals the slope m. We found the slope, it's 5 right here, so equals 5, and we keep the x. Remember, it's just a general x minus x1, and that was the given x value the one that they gave us. So minus that little x1 here is sorry, it's 2 right here. So x minus 2. And what this is basically we said, okay, we have an x value, a y value, we have a point on this function, we have a x2 and a y7, and it's a point right here, this 2, 7, and now we got the derivative of the function and put that value in to find the slope right here. And so the slope right here at 2, 7 is 5. We know that. But what if we wanted to see the tangent line? What if we wanted to get the equation of the tangent line everywhere that tangent line hits on the graph, other than just that point? So we know the point has a slope of 5, but what if we wanted to get that tangent line? And this is how we do it. So we take that slope that we got, we take the x and the y values, and we plug them in here, and we just crunch away and do some algebra. And so we'll just multiply the 5 in. That's going to give us 5x minus 10. And then we can add this 7 to both sides, and that gives us y equals 5x minus 3. And now we just take that function, that new function, that equation right there, y equals 5x minus 3, which looks really familiar. All we did was we converted this point slope form, and we converted it down to forgive me, I forget the name, slope intercept form, and we converted it to slope intercept form, which we recognize right here, y equals mx plus b. and we can just type that in, 5x, type it into Desmos right under our original function. So 5x minus 3. Remember, you don't have to do the equals. It'll just lay it out for you. Sorry, it's 5x minus 3, and you can see right here that they touch at 2, 7, and that's the only place they touch. So remember, tangent lines only touch the original function at one given point, or at one point. And in this, for this tangent line, it only touches it at 2, 7. And you could do that simply just setting them equal to each other, and setting them equal to each other and solving, and you would see rather quickly that it only comes down to one possible value, which would just be that they touch, and it'll give you the x value, and it would just be 2. It would say you would come down to an answer of 2 if you just compared. So let's say I wanted to say x, I wanted to find where these two touch without Desmos, just to reassure myself that it is the correct tangent line. If I didn't have Desmos right here, x squared plus x plus 1 equals 5x minus 3. And basically from here, you just combine. We're gonna throw. We know we're gonna have a quadratic over here, and so we can just throw everything to the left side and set it equal to 0. And when we do that, we'll have x squared plus, 5x subtracted from here would be it'd be x squared minus 4x minus 2 equals 0. And from here we'll just you'd be adding the 3 to both sides, and so it'd be plus 4. Okay, and that is set equal to 0. And as you can see right here, this is going to just factor down to x minus 2 times x minus 2, which will once again factor into x minus 2 squared equals 0. Let's not forget to equal 0 this whole time. And basically the only way to make this true is to set if x equals 2. So when we plug this in and say, 2 minus 2, this rings to be true, because 2 minus 2 equals 0, 0 squared equals 0. So that makes this ring true. And that's how we can check to say, where do these touch? At what point do these two functions touch? And that would be it right there. So we went kind of above and beyond here, but we really explored the tangent line, how to get the full equation to the tangent line, the slope of the tangent line, and the general point-slope form, and how to convert point-slope form to slope-intercept form.